Hello, class. This is Mr. Hart. And this podcast, we want to finish up the quantum mechanics unit. And no quantum mechanics unit would be complete without describing the standard model. Okay. Now, to describe what the standard model is, we have to look at kind of historically what we've thought about the world of the very small. Okay. So you probably learned when you were a kid that atoms are made of electrons and protons and neutrons, and the electrons orbit around the protons and neutrons, and they're in the center. Okay, this is obviously very false. Okay, we've learned, first of all, electrons behave like waves, protons and neutrons even have wave-like properties, and so it doesn't make much sense to describe it in terms of protons, neutrons, electrons, okay, and thinking about it just as particles. That's a very simple model developed by Niels Bohr, which at the time was great, but we've since then discovered a lot more. Okay, now instead of focusing so much about the wave-like properties, that's more kind of a chemistry type discussion with p orbitals, s orbitals, that type of thing. We're going to focus on the standard model, which is the particles that actually make up these guys. We used to think the atom was the smallest particle, then we realized that it had smaller particles inside of it, and now we realize that the protons and neutrons even have smaller particles inside of them, and there's other ones that we don't describe as often and that type of thing. Okay, so the standard model actually has 13 different particles that make up our world. Okay, now before we try and dissect this table and look at every single part of this, let's just focus on the ones that kind of make up the matter that we usually talk about. Okay, and so I kind of think of, for regular matter, okay, there's up quarks and down quarks. There's the leptons, which are electrons and neutrinos, and there's the gauge particles, the gluons and photons. Okay, once we kind of understand these guys, then the standard model will make a little bit more sense. Okay, so let's just try to understand these guys piece by piece, and then we'll go back to the full model and try and describe it. Okay, so let's start with quarks. Okay, so quarks, you probably have heard the word, but maybe not understood what they are. Quarks are actually a particle smaller than the protons and neutrons, and that's what they're made of. So quarks are fundamental particles that make up protons and neutrons. Okay, and basically how it works is the number of quarks that you have determines whether you become a proton or a neutron. So if you have two up quarks and one down quark, okay, then that particle is a proton. If you have one up quark and two down quarks, then that particle is a neutron. Okay, you can't have three up quarks because they don't come together without the down quark. And likewise, you can't have three down quarks because you need at least to have one up quark to hold them together. So based on how they hold together determines whether it's proton and neutron, and that's what it manifests itself as, and that's what we observe and see as these protons and neutrons. Okay, and so they are the most fundamental particles so far that we're aware of. Okay, that may change in a couple of years or whatever. You never know with quantum mechanics, but they're the most fundamental particle we know of that makes up protons and neutrons. Okay. And so that's quarks. They make up these kind of the building blocks of matter. Okay, the things that have a lot of mass and stuff like that usually are made up of quarks. Okay. Then next we have the leptons. Okay, and leptons are called leptons. They're categorized as these because they don't undergo strong force interactions. Okay, that's what holds the protons and the neutrons and the quarks together is the strong force. Okay. So if you don't have that, you can't build bigger particles. And that's what builds all the things we see around us, like lead, carbon, nitrogen, right? All the different chemicals, they come from the quarks and protons and neutrons. That's what gives all these big particles, right? If we don't have that strong force interaction, you can't do that, okay? And so that's leptons. They can't build anything bigger than themselves, okay? They kind of just hang out by themselves, which is why electrons hang out by themselves, because they're a lepton, okay? They are a fundamental particle. There's nothing that makes up electrons, okay? And so they are a lepton, and then neutrinos are also leptons. They are very, very small particles that are very hard to detect, okay? And they usually occur when there's some type of radioactive activity that occurs, if there's a splitting of an atom or a beta emission of an atom or something like that, okay? But neutrinos are just very small particles that come from energy conservation and things like that. Okay, but they're also leptons. You can't build anything with them. Okay? And then last of all, we have the gauge particles. Okay? And they're responsible for enforcing interactions caused by forces. Okay? So for example, gluons, okay, interact between quarks. Okay? They're kind of the manifestation of the strong force. So if the strong force is occurring, then they're exchanging gluons between each other, basically. Okay. And then photons, you probably heard of, they're light, right? But they are exchanged between charged particles. Okay. So photons interact the electromagnetic force. Okay. And so for most matter, we see that in the atom, right? We see the gluons interacting for the protons and neutrons. That's what holds them together. And then we have the photons, which interact from the electrons and the protons and the positive charges and all the different interactions we see that way. Okay. And so that is the gauge particles. They interact forces. Okay. And there we go. And so that's it. That's the fundamental particles that we know for kind of our regular matter. We got the quarks that build protons and neutrons. We got the leptons that don't build anything but are still pretty fundamental to building of atoms and things like that. And then we got the gauge particles that interact between or kind of cause forces. Okay. All right, so that's for regular matter. Now let's look at the full standard model, and now we'll be able to kind of dissect and see where these categories fit inside the standard model. So the full standard model is kind of described this way, or looks like this. Okay. And you'll see on the left side, you see all the particles we just described, okay, are kind of all the building blocks. So we got the up quark and down quark, okay, we got the electron and what's called the electron neutrino, okay. So all these guys are quarks, all these guys are leptons. Those are the ones for regular matter. And then up here you got the gluon and photon, okay. Let's try and look at everything else now, okay. So we have what are called charm and strange and top and bottom quarks. So these guys are still quarks. They still pair up in similar ways. Two charms quarks and a strange quark makes a certain particle and so on, okay? But these guys don't appear as often for some reason. In our world, on our Earth, we don't see this matter built up with these particles, okay? Now, I'm not a particle physicist, so I can't really tell you why that is, but we just know that these quarks also exist and they can pair up in similar ways, charms and strange, top and bottom, but they don't manifest themselves in this, area, however you want to say that, as much as the up and down quark, okay? Likewise, there's the muon and tau leptons. They behave very similar to electrons. They have a -1 charge, okay? But they're much larger, and they also have a very short lifespan. Okay, muons only exist for like 3 microseconds or something crazy, okay? And they have their respective neutrinos. So these guys exist, they're fundamental particles, but they don't have a very high lifetime or very long lifetime, and so we don't see them manifested as often as electrons. Okay, so we see this similar problem to these guys. So in all reality, these other guys exist, but most of our standard model that really matters to us is on this side. Okay, but just realize these other particles are here, but we don't see them as often because of their properties. Okay. Then we also have 2 other gauge particles. So we have the gluon photon, we talked about that. And then there's what we call the Z and W boson, okay? And they interact the weak force, okay? Now we won't talk a lot about the weak force. It kind of deals with, it's similar to electromagnetic force. It deals with kind of like radioactive materials, and it's just kind of hard to describe. But also sometimes in matter we'll see the weak force occurring, and these are the gauge particles that interact with it. So again, kind of the point, I didn't start with the full standard model because in reality, you don't really need to know a whole lot about this whole section right here. Okay, so these 4 quarks, these 4 leptons, and these 2 gauge particles. They're there. They're part of the standard model. They're fundamental building blocks, but we just don't worry about them as often. They're not as prominent. Okay, and the last part of the standard model, which is a new component, which is really cool, is the Higgs boson. Recent discovery, well, at least when I made this video in 2016, the Higgs boson was detected, and it's responsible for what's called the Higgs field. And it's similar to a gauge particle in a way, but it kind of interacts and determines how much mass something has. Basically, if something has more Higgs bosons or is interacting with more Higgs bosons, then it goes slower through what's called the Higgs field, and that means it moves slower in our classical world, which means it has more mass. And so it's just kind of this weird particle that gives things mass, gives things inertia, so they don't move as fast or take more force to move. Okay, but really cool particle, recently discovered, and probably by the time you may be watching this video, there may even be more on here. Okay, but that's the standard model. Okay, now before we go too far, one last thing to keep in mind though is the standard model is not complete. Okay, and one big part that's missing is the gravitational force. Okay? There's no gauge particle listed for the gravitational force. And so one reason why the standard model hasn't been fully accepted, why there's still some battle between the string theorists and the standard model people, is because the standard model doesn't have a gravity gauge particle. Okay? So some people believe in the near future, I should say most scientists believe, some are string theorists, but most scientists believe that someday we'll find another particle on this chart that they're going to call the graviton. I don't know how they'll abbreviate it, but graviton, okay? And basically it will regulate the gravitational force, okay? And there's some theories of why we haven't been able to detect it and things like that, but if we were able to discover the graviton, that'd be a huge step forward. It basically would complete the standard model and be consistent for all of physics, okay? It's one of the big things that's being searched right now in the world of physics is the answer finding the graviton, or is the answer describing these guys as strings, or how do we, finish the puzzle? How do we get all these pieces together? Okay, I'm more along the lines of thinking that, hey, they're going to find the graviton eventually, and then that will complete the standard model. Okay, but there you go. That's the standard model, and that's quantum mechanics. Again, quantum mechanics is crazy. The answers change a lot. We're discovering new things every day. But hopefully these 3 lessons kind of give you a good understanding and background and kind of a foundation to kind of do some more research and have a strong intellect about it. Okay, so do the homework. Hopefully that all made sense, and let me know if you have any questions. And thank you for watching.